go straight into it with 4.20 identifying intervals we teach. Today we're going to be analyzing a cubic function and a quadratic function. Let's begin. A function is increasing where the y values is increasing as the x values increases. So what that means is that if we read from left to right, where do we see this function going upwards? In which we have right here. It stopped going upwards at this particular vertex, and then we see it go downwards. And then we see it going it upwards again. For this cubic function, there are two domains that we will write when identifying where the function is increasing. Now when it's quadratic, reading left to right, it's starting to go up right after the vertex. Okay, and it goes on infinitively, right? That's why we have those arrows. And we write that domain as x is greater than 0. Now let's move on. A function is decreasing where the y values decrease as the x values are increasing. Therefore, where do we see this function lowering its y values? Where do we see this function going downwards? In which, for this one, it is right here. From the vertex to the other. And when we read left to right for there, it starts decreasing at the vertex. Okay, and we write this domain as x is greater than 0. And a really important key factor to identify is that they start increasing or decreasing at the vertex point and the axis of symmetry. If you ever wanted to justify your responses of how do you know whether or not the function is increasing or decreasing, please refer to the vertex point or the axis of symmetry, as those are the key indicators. That is when you know whether the function is increasing in the y values or decreasing in the y values. That is also when you see the function is going down or is going up. That's like our starting point or ending point, right? Because if you look at here, it's a starting point for when it's increasing, but if for decreasing, it's the ending point. Okay, so the vertex point is when the function starts, when it's increasing, but it's the point where it ends, where it is decreasing. Now let's move on to when the function is positive and negative. A function is positive where the y values are above the x-axis, meaning that all these y values must be positive. Looking at this function, it is above the x-axis. Here to here, and here. Okay. For this quadratic function, it is above the x-axis. Going upwards here and here. And we write this domain as when x is greater than 1, describing this area, as well as x is less than -1, describing this area. If it helps, what you could do is shade in all the area above the x-axis. Okay, above the x-axis, to identify when it is positive. And where it is negative, you can use a separate color to describe when it is negative. Okay? So let's do that again when a function is negative, where the y values are below the x-axis. So for this function, let's color that in. It is below the x-axis from, say, and it is below the x-axis over here. So let's write this in for the domain. X is below the x-axis. X is under the line here. From, say, -1, any point less than -1.5. And because it stops being below the x-axis to be above the x-axis, so we cannot include there. But it's also negative from x is greater than +1.5. Now the key term to justify your responses of how do you know whether a function is negative or positive is not just by identifying the x-axis, because if you look at our values that determine whether it's whether it's positive or negative, they are the same values as the x coordinate of the x-intercept. What that means is this point right here is -1.5, 0, and this point right here is +1.5, 0. Therefore, for this example, it is negative all the way until that x coordinate of the x-intercept. Therefore, it is negative all the way until that x-intercept, and that's where it ends. And here it is negative starting from the x-intercept going into infinity. And as for here, again, notifying, it is the x-coordinate of the x-intercept. The story begins when it's positive from infinity all the way until the x-intercept at this point, and it is positive starting at the x-intercept of this point going infinity, which is why we use these two values. As an extra opportunity, state the domain where the functions are increasing and decreasing, and when they are positive and negative for these cubic functions. You can either write that in the comments section or make a private comment on Google Classroom. Let's apply this knowledge in example 1. Determine the intervals for increasing, decreasing, positive, negative, domain and range for the function with the given points that are described as letters. Okay? So let's begin. Where do we see the function is increasing? Where do we see where the function is increasing the y values? Where do we see where the function is going upwards? Right? And it is from point D all the way to infinity. Therefore, we write it as x is greater than D. Now, where is the function when it is decreasing. Where is the function where the y values are getting lower and lower as the x values are getting higher and higher? So your responses is all the values from infinity all the way to coordinate D. See how I'm getting lower and lower in my y values? And I'm getting closer and closer to the x-axis, right? Because this is 0, 0. So here we have like a -6, -5. Now I'm at -4, closer to -3, -2, -1. Okay, I'm getting closer and closer to a greater negative value. Therefore, it is decreasing. We can either say from -infinity, comma D including, or x is less than D, not including. So now we color it in when it is positive, when we color it in as negative. It is positive when it's less than B, the purple area, and it is positive when it's greater than F. Now looking at how we colored in the pink side, which is below the x-axis, we also identify the two x-intercepts. Therefore, we use them in writing our notation, and because it's in between B and F, the function is in between B and F when it's below the x-axis. We write the function notation as B less than X less than F. Okay? This means it's in between, and we only need that one interval. Now let's go into identifying when the function and its domain. So the question we have to ask ourselves is, well, when does the function start? When does a function end, looking from left to right? And because this is a quadratic function, we have two arrows indicating that they both are going infinitely on the left side, going -infinity. Being as though this is a quadratic function, we have a parabola with two arrows, in which one's going on the left side, so it's going to -infinity, and we're going all the way to the right side to +infinity. So we write that notation as -infinity, comma infinity. What that also means, because it's inclusive to all points from -infinity to infinity, we also state that it's all real numbers. And that's what that symbol means. All real numbers. And it's justified by the fact we have arrows, which is an important feature to graph. When we are identifying for range, we always look at the y coordinate of the vertex point. Okay? In this case, we're just going to leave it as D. And we have to ask ourselves, from going down to up, when does it end? Because it starts at D, right? And again, the arrows are the indication. It goes to infinity. Well, now we have to ask ourselves, from the y coordinate of the vertex point, just going upwards, does it ever end? Looking at the arrows, the answer is no. And this side of the graph is always +infinity. Now we write the range as y is greater than or equal to D. Opportunity. Where are the roots? The vertex point, y-intercept, axis of symmetry of this function. Okay, I want to see the letters and written in the proper notation format. Now let's get into example 2, where we're given this negative quadratic, right? It is concave downwards, because you can see that the function is opening up downwards. You can also say it's concave downwards because the arrows are pointing downwards. Alright? Now let's go on to when is it increasing. We start from increasing all the way to what seems to be x equals 2. Therefore it's increasing every value less than 2. And I say is x than less than 2 because from here, negative 2 is less than 2, negative 1 is less than 2, 0 is less than 2, 1 is less than 2. Right? Even 1.5 is less than 2. So all of these points going upwards is when it's increasing. Opposed to when it's decreasing, right? It is x is greater than 2, right? 3 is greater than 2, 4 is greater than 2, 5 is greater than 2, infinity is all greater than 2. So write those two notations as such. So looking at the x-intercepts, this one and this one, where do we see that it is positive? It is in between 1 and 2. So we write 1 is less than x, is less than 3. Sorry, between 1 and 3. Therefore you write the notation 1 is less than x and is less than 3. Again, this is between. Now when it is negative, right, it is all here, everywhere below the x-axis. Right, everywhere below the x-intercepts. So therefore we write this as x is less than 1. Because it's negative all the way up to 1. But also looking at this x-intercept, it's also below the x-axis as at 4, at 5, at 6, and infinity. So we also write it as x is greater than 3. When are the points are being included in this function? Looking at the x values. Well, because we have infinity, every x point, we keep on going, it's going to be inclusive to all negative x values and all positive x values. So again, we have all real numbers from negative infinity to infinity. And with the range, we look at the vertex, which is right here, the y part of the vertex, which is 1. So this is what, because it is a negative x squared, it's going downwards. So our range begins at 1 and it ends, well, again, we have we have 2 arrows, so that indicates that it's forever going downwards. And when it's going forever downwards, that means we're going on the y values, it's going to reach all the way to negative infinity. It's never going to end. Therefore, from 1 to negative infinity, we write the notation y is less than or equal to 1. Extra credit opportunity. Looking at this graph, where do you see the roots, the vertex, y-intercepts, axis of symmetry of example 2 for an extra credit opportunity?